Great. Thank you very much. My name's Will. It's a great pleasure to introduce Professor Terry Yi. He did his undergraduate at Tsinghua University in China, which I think is the top-ranked university in China. Then he did his PhD at Stanford, which has quite a good reputation. Since then, he's been working in a lot of different industries in Silicon Valley. So he's done a mixture of industry work and academic work. He's been returned to China. So for the last decade, he's been at the Southern University of Science and Technology. He's also the chief scientific operating officer of Internet of Things Lab at Hong Kong University. So he's going to give a really interesting talk about passive and batteryless sensing and actuation for e-textile and devices. So that's really relevant to anyone who's an engineer, who does textiles, who does sensing, or anything like that. So,
okay. Yeah, thank you, Will. Yeah, thank you, Professor Guido, for the introduction, and thank you for the IAS Institute of Advanced Study for inviting me here for this week as a fellowship. And it's a really great honor to be here. And I know some of the people I met yesterday, and some of people I have quite interaction with. And the story with my connection with Loughborough is just a beginning of this year. I think I made a excursion trip from a conference in London, and I came here and I talked to Will, and we had quite a lot of synergies, working in various projects. So that's why he invited me here again back for this week for have more interactions. And over the past week, I had a really busy scheduled, meeting, almost a meeting with the different professors every day. And I have a really exciting week, to know about professors. I also expand my scope of the knowledge to different disciplines. So today, actually, I'm really honored to be here to present my work in the field so-called e-textile devices. And I remember Will once yesterday, he asked me what is my expertise. And actually, it's really a little bit hard to say because I started my background as a chip designer, a semiconductor chip designer. And then I worked for a company in Silicon Valley. And later, there's a company I worked just before I went back to academia. It's called Impinj, which I designed the world's first RFID chip, transponder chip. And then, so that put me into the RFID and NFC technology. And because that technology the wide application of that technology is to use on the garments and the clothes. So I have to design my antenna and the integration into the garments fabrics. So that moved my direction from semiconductor to the fabric and the garments. And then I began to get very interested in e-textiles because I feel like e-textile is really a new domain for applying electronics. So we know that, and right now, almost everyone has some kind of wearables around their body, right? So like a watch or wristband. So we have many wearables around, either as entertaining or as a serious medical, monitoring or tracking devices. So if you wonder, we have so many wearables, actually we have not enough, because in the years ahead, projection says we don't have really more variables around our body to perform different functionalities, for entertaining, for sports, for training, for rehabilitation, or for medical monitoring. So the problem is how can we put all those sensors or devices on our body? Well, one natural thought will be we put those devices on the clothes. So that's make a smart wearable devices, the so-called e-textile devices. So that's the name comes from. Very interestingly, because when I talked to Will, I think 2 days ago, so I said we are working on electronic textiles, and Will said, well, why don't we call it textile electronics? I think that's a really better concocted name because you see, wearable electronics and also textile electronics seems like a new field of electronics rather than new field of textile, because I'm from electronic background, right? So I think that from now on, I would use a new concocted term called the textile electronics. That's for now. So what's the advantage of doing that? Well, you know that once we put a sensor devices on clothes, it's non-intrusive. It's long-term because we don't feel it's wearing. So in long-term and in real time, It's aesthetic, it's like we don't feel like there's like some device in between. And there's another nice feature is those e-textiles that do not have to scale with Moore's law, because we know Moore's law, like they shrink the size every 2 years by half, shrink the size by half every 2 years. But we know our human body so keeps the constant form factor. So, well, that means our devices can keep like a constant shape. Okay, so if we want to build like a e-textile devices along the clothes, we have to utilize existing construction methodologies of textile, like weaving, knitting, embroidering, or braiding. Those are the traditional the construction technologies. Because if we do not use that, we won't build a device that feel like fabric, right? So the e-textile devices constructed from those traditional methods, we can make like interconnects, antennas, inductive coil, and or even sensor actuators, or like other devices we can imagine of. So today's talk, I'm going to explore what can be made using the traditional e-textile or textile fabrication construction, the technologies. So you see, there are many challenges in constructing e-textile devices, right? The first challenge is how can we connect those devices along our body? So that's the first challenge is how can we connect those devices along body? So we have to see those fabric interconnects has to be fabric based. So transmitting signals and power supplies and also data links, because right now, like we have many digital like gadgets, so they need to transmit the SPI, UART, those some names. So and those devices are interconnected into a body network, body area network. We call the BAN, body area network. So that network has to be flexible, stretchable, and resilient to some wearable conditions like moisture or even endure for the washing cycle. So, and that's the first challenge. Challenge number 2 will be how can we power up those devices, because every device needs some kind of power. And if we put the batteries in like any of the devices, it's going to be a disaster, right? Because we cannot, even for my cell phone, I forgot to charge it every day. And not mention we have 10 devices. It's a really a disaster to charge 10 devices every night. So the convenient, so the traditional battery or like a traditional way of powering up those devices will be inconvenient, inaccessible, and intrusive. So, well, we have to find a new way to power. And the third, so those those challenges. So solutions, well, there are of course there are many other solutions, but for my research, I'm proposing solutions to use a passive sensing. What do we mean by passive sensing is for active sensing, there's like a battery, the transmitter, and also the transceiver. So there's like active communication between like a sender and receivers, just like your cell phone or like your walkie-talkie, like the two-way communication. But for passive sensing is, well, there's a passive sensor that one has no battery, has no power, but there's like an incoming like electromagnetic query or signal that can get some kind of like a modulation of the sensor and then reflect it back. So in this way, the sensing information can be modulated in the backscattered waves, while the sensor itself does not need any battery or power. So that's why we call the battery sensing, passive sensing. Another solution I'm proposing is to use a batteryless device. So batteryless is different from passive. Passive means there's no battery needed. But the batteryless is like we still do not need a battery, but we do need some kind of energy. So those energy can be harvested from the ambient, like the lighting, like the sunlight, or like the movements. So all those ones are ambient energy. So the batteryless devices means we energize the devices with the energy harvested from the ambient, like the sources. But here's the problem: is not all sources can be harvested, and even if we can harvest, the efficiency is still quite low. So, well, that's the problem we're going to solve. And so here, because my background I just introduced is I'm good at NFC RFID technology, and also it's a technology widely is very available. So I'm proposing to use RFID and ANC technology for passive and batteryless sensing. So here's like, we forget about the technology details, but there is something you keep in mind. There are two like a way of RFID or like a, so the first one is called RFID, but in the wider definition. So that one can sense or read, interact with your devices, like from a few meters away to a few, like 10 to 20 meters away. It can harvest energy of around 5 microwatts. And the NFC function, just like every cell phone right now, they have an NFC function. So that the interaction is about a few centimeters away, we can harvest power around 10 to 30 milliwatts. Well, milliwatts actually does not sound a lot, but for like an electronic engineer like myself, a few millimeters watts means a lot. Actually, we can do a lot of electronic functions with that power. So here's just like a very simple definition for what do we mean by NFC. Actually, because of near field communication or NFC, every cell phone right now we have a NFC function, but that definition is really vague because NFC, when broadly used as a technology term, it only means literally near field communication. That means any communication within one wavelength can be called NFC. And but when we use, like in these days, when we use NFC as a protocol, a commercial name, it only means operate at the 13.56 megahertz following the standard called NFC forwarding. So in this talk, actually, I'm going to use these two terms like in the mixing fashion, because sometimes I refer to near field in the technical term. Sometimes I mean NFC in the protocol term, but I think you can sense the difference when I'm talking. Okay, so here's that's enough for the background. Today I'm going to split my talk into 3 sections, and hope I have enough time. So the first one will be how can we construct fabric-based interconnects? So how can we use a simple conductor wire to construct devices? But what's the property of the wire of the conducting yarn? And the second is how can we construct fabric-based passive sensors, like or even we can put the chips into the fibers. And the third one is about the battery-based devices. How can we use a smartphone as not only as an entertainment or as a communication device, but as a medical assistant or like an energy devices that can power off some kind of like a little electronics that can perform some like a sensing or therapeutic functions. So those are the 3 sections I'm going to introduce. That's the first one. Well, because once we talk about the e-Textile, once we talk about the textile, we have to first talk about the yarn or the fibers, because that's the basic element to constructing any textile like the structures. So right now the conductive yarn are often used as simply a replacement for mechanical wires, because we just use we have a wire, but that's too rigid. Then we have a conductive yarn, which is like a fabric and also soft and bendable and stretchable. So that can be constructed as a construction material for the interconnects, antenna, and all the other things. Okay, so but the problem is actually the conductive yarn is not simply a wire. It's not simply a mechanical wire, because that's different from a mechanical wire. We know by our practice, we know that the devices made from conductive yarn are inferior in performance as compared to the real mechanical wire, like they have a low Q factors or low inductance or higher resistivity, because here we do some measurement. We construct a conductive yarn, use a conductive yarn to construct a coil. We can measure the inductance, and we find it's constantly inferior to that as compared to real metallic wire made in inductors. So why is that? Well, here's we do some a microscopic study. We find out the conductor yarn are really a bundle of conducting filaments. And there are many gaps between the filaments, and we know those are filaments actually. The gaps can form the capacitor. So that's we call it a parasitic capacitor. So those little capacitors really deteriorate the performance of a conductive yarn. So how can we characterize those like the parasitic capacitors, because we know that the parasitic capacitors just is spread around everywhere and in every gap. So it cannot really quantify the value of every single one of that. So here's before I introduce further, because if you're not from electronics, it's okay. But here's just said, if we want to measure the capacitance, here are two capacitance. One is called structural, because once we have two wires, there's some capacitance, that's called structural. So that exists there. And the other is, besides of the structural capacitance, if you have little gaps in between, that will form parasitics. So parasitics is put it in addition to those structural capacitance. So right now, our work is how to extract this part. Because this part, the C part, that's a structural, is common to every structure. Doesn't matter it's a metallic or it's the metallic or other material, it's always there. So, here's a simple idea before we go to any technical details. So we can measure that using two identical, the coil or the helical structure or the air core helical inductors, because we can construct two inductors, we call the helical inductors, with the same geometry, the same number of turns, the same gauge of wire, the thickness. So everything is the same. The only difference is one is from the copper wire, one is from conductive yarn of the same thickness. So if there's any, because this one can resonate, it's like a resonator. So if there's any difference between those resonating frequencies, that difference has to come from the parasitics. So that is a theory, or that is a method we use to extract those little parasitics. And here's some electronics, we just forget about that. But if you are interested, we can go back to this slides to talk about some circuits. So the problem is, so we use we measure the resonant, the resonant frequency, so we can extract the capacitance difference between these two yarns. And that's only, because that's only one measurement. We can only measure one wearable. That's so we call the lump sum parasitic, because we put all the parasitic effects together as a lump sum, we can measure that. And there's another way we need to measure each of the individuals, the segment we call the unit length. So in this way, we can measure many different frequencies, different variables, different frequencies to have a curve matching. So that in that method, we can measure each of the individual unit length parasitics. So here's forget about the details. So we use three different kinds of wires. One is a stainless steel conductive yarn, and the other is another gauge of stainless steel with a little thicker. Yeah, another is a coated polymer conductive yarn. We call the composite one. So here's some measurement. So just you don't have to look at the details, but you only remember the difference between that red line and blue lines are caused by those parasitics. So by measuring those differences, we can extract the lump sum, the parasitics. So here's some the outcome of the measurements. So for different ones, we can measure each of the unit length parasitics, and also as well as the total lump sum. And so those numbers are too technical, but here's a message, a simple message I try to deliver. So for this kind of conductive yarn, we call S310. It's about every centimeter, there's about a 2.3 femtofarad for the conductive, for the parasitic capacitance. So this one is a little bit a denser, it's about 0.87. And for this one, used by the polymer composite yarn is about really big, it's about a 3 femtofarad. So those ones are little parasitics. But for the people like me working on the electronics, working on the signal transmission, those ones will make a big difference. So that's why the purpose, why we're doing this measurement. Okay, so once we know that, there are so many parasitics for the conductive yarn, can we do something to improve that? So we construct a new conductor yarn called silver plated. Actually, it's not quite new, but we do some like a enhancement. So the core, conductor core is consists of, there's a copper core inside, that is a silver plated. The reason why I have a silver plating is we want to solve the skin effect. The skin effect is, we know that for the electromagnetic point of view, that once we go to high frequency, the current will concentrate more on the skin rather than in the core. So that's called skin effect. It's only happening in a high frequency communication. So by doing the silver coating filaments, we can tackle this problem, the skin effect. And then we wrap that with some thermal insulation and also protection layer. And in comparison with like metallic filament, we can see this kind of interconnect has a pretty much better performance in the transmission. Here's we measure, they call the S21. S21, yeah, just forget about the name, but the purpose of this measurement is to measure how well the signal can transmit from one end to the other. So we can see that we have like almost like 6 dB better, or sometimes in the high frequency 3 dB better than the traditional conductor yarn. So 3 dB actually means we at least the energy is saved, is like we have like a more double the energy that can be transmitted. But the silver plated yarn is not flexible, it's not stretchable. So how can we make the yarn stretchable? Because that yarn needs to be like a conformal to the body movement. So we do some experiment. So based on the silver plated conductor yarn, we like wrap it or like make a spiral wrapping or the coil around a spandex filament inside the board, because we know spandex is like elastic. And then we can make a high elastic conductor yarn that can be used for conducting long range or long distance signals. So here's some details, material details. And so this research is still a ongoing research. So we can see some measurements. So by using the high elastic conductor yarn, the performance is almost as good as the silver plated one. A little inferior. Well, it's understandable because you see that for the helical structure, for the same linear, the special difference, the distance, we have like a more like a linear length because it's a spiral structure. So a little bit more resistance, but that resistance actually is not much. It's worthwhile because it's only here's the difference. Like 1 dB or 1.5 dB is compared with the traditional, not traditional, the silver plated one. So, but the benefit is this one is a high elastic. So we sacrifice a little bit conductivity and gain a lot of elasticity or like stretchable. So that is really good for the wearables. And this one is still ongoing research. We are trying to build a elastic on-body area networks. And another benefit of this like a coil structure is the crosstalk. The crosstalk is a technical term, but it simply means like two wires are running in parallel. While the signal on one wire can interfere or cause the interference on the other wire. So that's called the crosstalk. And we find out that actually there's a nice feature or side benefit of this coil structure, because this helical structure actually have a less like a radiation leakage on the side. So that one has a much less crosstalk these impacts as compared to the traditional like single wire. And so that's why it's a really good when you have like a in bus running on the fabric. And so that's another benefit. It's still ongoing. So we try to have a more interesting measurements. Okay, that's for the first part. We call about how can we construct a interconnect. The second is how can we construct a fabric-based passive sensor. And here's I introduced two methods. One is like how the sensor directly constructed from fabrics, and the other is a chip how can we like embed or hide chips inside the fabric. And again, so we just review back to the NFC technology and RFID. So we can, for RFID, we can sense or interact with the sensors a few meters to 10 meters away with the power of a few, like a microwatts. So that's the RFID technology. And but the people, we have heard RFID technology a lot in the past years that, but nobody probably few people aware that RFID chip or semiconductor chip are the largest deployed semiconductor chips in the world. And even last year, last year alone, in 2023, there are around 45 billion tags or chips just like utilized somewhere around the world. So you may not notice that almost every garment or every like the clothes or maybe like some of the drug bottles, they have a hidden chip inside. So that's RFID chip. Right now there are just 1 year alone. Last year there are 45 billion RFID chips. So there are two mechanisms for communication for RFID. One is called backscatter. The simple term is like we have a reader just sending the signals, and then this signal is a power of this chip, and then the power up is changing the impedance and reflecting back the signal. And then the information can be encoded in the backscatter. So this way, you see, there's no battery inside. The reader, by the way, is just like a sound reader in here. Just if you put this reader just beam it a few meters away, you can read the tag information. So you can see, and so in this way, it's called backscatter. Another way of communication is called inductive coupling. So inductive coupling is they use a two coil to like there's a electromagnetic field just like a couple in between, and if the chip can still be powered up by the coupling, and once it's powered up, there's a function inside, and this function will change the impedance of this coil, and then the reflecting or the coupled back signal can be modulated. So that can extract information from the coupled signal. So that's called inductive coupling. And so both of the mechanisms are widely used in today's RFID system. For long distance, we use the backscatter, which can be good at like 10 meters away. And for near range, we can use an inductive coupling, which like a few centimeters or 10 centimeters away. But why do we want to use that? Because sometimes inductive coupling is good to transmit or go through the waters, because magnetic field can penetrate the water. So it's widely used in the near field. Okay, so here's some like interactions. So the idea is, hey, if we can utilize the RFID tag as a sensor, and then when we put a RFID antenna just around in the surroundings, we can find an easier way to sense the information from human, like either their gesture or their movement, or even their body vital signs, like a respiration and heartbeat. And by extracting the amplitude, the phase, and or the Doppler shift. So that's the idea of RFID sensing. And there's a three way we can extract those informations. Either the sensors can be powered up by the RFID and encode the information back in the chip and then back to the reader. Or that's the first way. Or the second way is we can put a sensor on the antenna. So the sensing information can change the impedance of the antenna. So the backscatter or coupled signal can carry the information of the sensing information. So this one is called impedance modulation. That's a way number two. Or there's another way. So those like a sensing information can cause some kind of like a path change, transmission path change in between. So the signal can be, or information can be sensed by the reader. So that's called path modulation, or there's like a path. So those ways can be used altogether to extract information from these passive devices. So it's just like that. When we receive the signal back, we can extract information. So what's the difference between a RFID-based sensor And the sensor we see like a Bluetooth or like a Wi-Fi sensor. And the first is like is passive mode, right? And one of the basic big difference is each of the sensor, it can be associated with ID because RFID has a naturally have ID information. So those are sensing information can be carried along with the ID information. So that sensor naturally will have ID associated with that. So you see those RFID based sensors, they are really long life cycle because there's no batteries, low cost. Every tag is like a few cents of US dollar, a few cents of US dollar. It's really cheap. And it's identifiable, it's a wearable, and it can be embedded into the daily objects. So here's like some of the method. We can construct a fabric-based RFID sensor. We can use a fabric like the embroidery technology, use a conductor yarns to construct the antenna. The antenna, some part of the antenna is stretchable. So by making the stretching or the displacement, the impedance of the antenna can be changed. So the backscatter can be modulated or interfered by the displacement information. And here's like some of the technique we use a conductor yarn to construct those like antennas. And it can go through a really standard embroidery machine. And you see, when we put this kind of sensor on the knee or on the elbows, so you can see that the movement of the body can be like a tracked. And so you see those sensors are really made of fabric, so it's really feel like just a normal clothes or fabric. It doesn't feel like there's like a solid state object that impede your behavior. So that's a fabric-based movement tracking. And the other way we can construct that, we can make a two like a coplanar coils, and the displacement between those two coils will cause the inductance, the equivalent inductance to change. So that can make another displacement sensor. And so this one we can also use just a traditional fabric, the construction method using embroidery. So you can see that the displacement will really related to the inductance change, which will relate it back to the signal that feed back, that coupling back to the reader. So once we put this kind of like sensor just on the waist, so we can sense the respiration, the movement of the chest. So that can be used as a respirational sensor. And so those ones are two examples. Actually, over the past few years, we have constructed different fabric sensors. So those are two examples. So people may ask, because this kind of sensor relies on the RSSI or backscatter signals. And we know that by instinct, by intuition, the backscatter signals are really not reliable because there's so many interference in between the reader and the tag, like the ambient movement or the change or some kind of like the movement or like even the temperature change. So how can we remove or like reduce the interference from the ambient? And here's one way we can use a differential or pair of RFID antennas. Just simply speaking, here's an example. So we can make two antennas. One antenna has like a kind of like a positive response to the like a deformation, while the other has another negative. That means that like once we stretch an antenna, we can make one antenna that will decrease as the stretching goes on, while the other antenna will increase. So these two will be differential. By using the differential signal, we can extract or eliminate the ambient common mode noises. For example, here's like one test we have done, and we have two tags, and this, like you can see that there's a common background, like a movement, which is common. And we cannot see much from these two backscattering. But if we take the differential, we can see, well, that is the information that I extracted. It's about the movement. So here's one example. We can put this like a differential tags on the clothes. And once the people perform some kind of movement, so we use a differential signal, we can clearly see some of the little bit of detailed movements, like in the on the this sports the lady stretch her legs, so we can sense the difference. And here's another example. We can put a tag on a facial mask and also put a two differential tags on the facial mask. One is sensible, one is not so sensible. By using this differential signal, we can sense the respiration, the movement of the people, like when they're breathing in and out. So here's like a one of the applications. One by putting the like RFID sensors on the mask, and we put the readers a few meters away, we can sense the breathing activity of this of this person. So here's that part. You can see that those like a sensor are still a little bit like, although it's a made of fabric, but it's still like you can feel there's something there, right? It's not really like an invisible or like a concealing. So can we do something even better than that? Well, here's can we just put the chip directly into the fiber? And so because before the previous approach is the one people put the circuits on the fiber or on the fabric. They just attach the circuit directly on the surface of the fabrics. So they are detached. It's not really hidden. So you can still feel there's some kind of like a solid state circuitry. And our approach is, well, that's some recent work we have successfully achieved in the past few months. We can embed like the little chips and sensor chips along with the filaments, and then the filaments can be braided just along some other wires. We can make a yarn or wire, then there's a chip inside. Of course, those chips are really like a small chips, like RFID chips or NFC chips. It's not like a CPU or GPUs like big one. We are not talking about those big chips. We are talking about the little tiny sensor chips. So it's made into a yarn like structure. Yeah, so this yarn-like structure can really go through a traditional embroidery or knitting process. So here's like this yarn, it's really flexible and really just feel like a wire. So it can go through a knitting process using the knitting machine. And so you can, in this way, this one, just for the purpose of this PPT, we use a black one, but actually we can use a white one. So once we use a white one wire for the knitting, it's invisible, you cannot see that. So that's a nice way to conceal those little like sensors into the garments. And here's some like interesting research we are going on, but I think that's later is some details. So that's actually a new method for constructing the knitting antennas. There's some like a nice structures, but it's still going on work. For example, once we stretch the horizontal way, the resonant frequency will go up. Once we stretch on the other way, the resonant frequency will go up. So that's a kind of, they have a differential behavior. If we stretch in different way, it's still ongoing work. We try to utilize those structure difference and as another sensor. So this sensor actually is different from the previous one because this sensor is truly invisible and is embedded into the yarn or into the wire or into fabrics. So here's like I think one video, just a very short one, just a few seconds. Where's my folder? Yeah. I need to stop it. Yeah. Okay. So we can so we can sense the movement. We built that. That's the sensor we use, like the wire sensor or the yarn sensor. So it's embedded into the cloth. So you see, we sense the movement about 5 meters away. You can see the leg movements. So that's a small video.
Yeah, we can swap those as well.
Okay. What?
I'm sorry, just to.
Okay. Okay, so we can not only embed a little sensor chip. Actually, we can also embed or put a little micro LEDs into the fabric. So so by putting LEDs, we can really make that illuminated or like LED like the mark the yarn. So this yarn is like the diameter is less than 1 millimeter, and it can be like embedded into the fabric. And so we can make the illuminated like the fabric. So that one can be used as a marker or as maybe a fashion clothes. Yeah, maybe you have more imagination than me. So the advantage of the tradition compared with traditional one is that this one you truly feel like it's a natural fabric. You don't feel like there's a light bulb inside. You feel like some kind of like a rigid. So you can perform many like a normal activities, and while with the little LEDs just light up in the dark, or you can use like special cameras to capture those lights. And I have a sample here. If you're interested, you can see that we have like put those little LEDs in the glove, and the glove can be light up. And yeah, it feel really natural. So, sorry, why is I'm going all the way to the end. Okay. Okay, yeah, I got it. Okay, so that's the second, and I hope I have a little time for the third topic. So the third topic is about we can use a cell phone as a better assisted device to perform like many little very interesting functions. So that's the previous slide is about using RFID on this part. Now we use the cell phone NFC functions on this part, because using NFC functions, we can harvest around like a few tens of milliwatts. And we did some measurement, just using a simple cell phone, putting that up around 10 centimeters away, we can, by connecting different loads, we can have a few like a 20 to 30, like depend on the power of milliwatts. So what can we do with those harvest power? Well, here's like one, we can make a body fluid sensor, like a sweat sensor. We can put a circuitry inside and put some kind of sensor that is sensitive to either the pH level or the sodium level or even the glucose level. So we can make that as a as a fluid sensor. So here's one of the pictures with it. So we build a sensor that is totally powered by the NFC function from the cell phone, and also the reading can be transmitted back to the cell phone. And the advantage of that is that there's no battery inside this part. So that can be made into the form factor of a band-aid. So, and it's have a really low cost. And using this one sensor, we can sense the sodium level or the pH level or pH level or the glucose level and of the sweat. Of course, people may argue that the glucose, the from the sweat is not quite a good indicator, but that's a medical problem. It's not my problem. So, but the message is that we can sense many fluid, the signs from around the skin using this like a cell phone paired with the like a little passive battery-less electronics. And here's another bandage, we call it e-bandage. We can integrate an array of sensors into this flexible electronics. And those array of sensors, a temperature sensor can be used to monitor the heating process, because we know that the wound area, the temperature is higher than the surrounding healthy skin area. So by comparing the temperature difference, we can monitor the progress of the wound healing process. And in the same time, we can also put a near infrared LED array around the wounded area. So we know that the near infrared will expedite or speed up the healing process. So by combining these two devices into this like a band-aid, we can make a so-called e-band-aid. E-band-aid can speed up the healing process. In the same time, we can also monitor the healing process from a cell phone. And so here's some like a medical research that prove by using a certain wavelength of infrared, that can speed up the healing process. And actually, we did this experiment using a lab rat. And we can have a control group, we can see that using this near infrared treatment from a cell phone, the healing process will be around like if the healing process for normal wound will be 10 days, we can heal that around 7 or like we can like speed up by a few days. And here is like one little video I'd like to show. Yeah, we can monitor the temperature difference. Oh, yeah, that's a short one, but you got the idea. Okay. So okay. So this one can not only can be used as a just a normal bandage, it can use like for the places where you getting the monitoring wound that it's not convenient because when like people get as a plaster like for fracture. We can use this one to monitor the progress inside the wound, like and read the information out from a cell phone. So you can see this one is really convenient. We turn the cell phone into a personal medical assistant device. And here's another the usage we can also build a electromagnetic pulse generator with the energy harvest from the cell phone. And this cell phone can administer the pulse frequency and the width and also intensity. And then so that one can be also built into the form factor of a bandage. And that bandage, we know that from the previous medical practice, we know the electromagnetic wave, the pulse, can help to ease the pain of the muscle. And it can also expect the speed up the wound healing process of the cutaneous wound. So that one can be also made into another form of e-bandage, which will help the skin, will help to counter many of the skin diseases. So here's some of the experiment that we do. And here's an interesting one. We also measure the electrical field that can be generated from this e-bandage. People normally by instinct, they will say, well, the signal or the energy is too weak because like a few tens of milliwatts may not be enough. But remember, we are not talking about like a huge devices that for like a full body treatment. This one is only good for the spot treatment, only treatment for the spot. So by concentrating the electromagnetic wave or the infrared to a certain spot, the intensity of the field actually is comparable to the big devices that have the whole body treatment. So here we can compare that the electrical field is around like 1,000 volts per meter, which is comparable to like a bigger devices. And this device is just like a spot treatment. So here we perform another experiment. Like this one just got accepted by the NTJ digital medicine. So we prove that by using this kind of a field of electromagnetic wave, and that will help the healing of the wound. And we also did some experiment on the rat with these devices powered from the cell phone. So you can see the wound is speeding up like by for a 14-day cycle, it can speed up by 4 days or even 5 days. And for the people in the field or the people like in the wild or in the military, like a combatant, so that a few days difference actually can make a really big difference with the life and the death for people just working in the field in the wild. So here's some like a comparison between different modes of different field of different electromagnetic pulses. How much speed up can we have? Okay, so I think that's how I'm going to wrap up my talk. So in this presentation, I'm like introduce like 3 different sections of like e-fabric or e-textile devices. First, how can we make a good conductive fiber that can have a good performance incomparable with some metallic wires. The second is how can we construct a passive sensor using the embroidery knitting or like the braiding, the traditional fabric, the construction of the methodology, and how can we embed the chips into the fiber. The third one is like how can we use a cell phone not only as a communication or entertainment devices, but also has, in the future, we can use a cell phone as a personal medical assistant device. We can perform many of the like medical monitoring or therapeutic functions. Okay, so I think that will conclude my talk. Thank you.